In the first video of this series, entitled A Cyclical Universe, it was shown that a cycle like the phases of the Moon can be expressed in terms of a uniform circular motion. At that time, it was argued that from our point of view we can observe the cycle of the Moon from the outside, and therefore we can see at the same time both the light and the dark sides of the Moon. But in the case of the universe, since we are a part of the structure, it is impossible for us to simultaneously see the presence, that is the illuminated part, and also the absence, that is the dark part. This perspective from within the structure implied the entry of the imaginary unit into our analysis. In this way, the expression that characterizes the circle turned into the equation of the hyperbola. And the expressions of the change of coordinates due to an axis rotation became the starting point of the hyperbolic theory of relativity. Therefore, at this point we made an interesting nuance. Instead of understanding the fabric of the spacetime as hyperbolic, we said that its original geometry is circular, but the fact of observing it from within the structure is what makes us see it as if it were hyperbolic. At that time, the functions a star cosine and a star sine were defined on a triangle with the vertical side being imaginary. Expressing this inner view of the change of coordinates as a function of a velocity v sub g, which was previously defined, one obtains the Lorentz transformations. Then, in the second video of this series, we wondered how the Lorentz transformations were seen from outside the structure, that is, what is the aspect of the conventional change of coordinates due to an axis rotation when written as a function of that v sub g. In this sense, it was shown that those expressions, although different, are quite similar to the Lorentz transformations. In particular, it was argued that that difference in sign within the square roots is not relevant, as it acts as a sort of a scale factor that influences both expressions. The sign change that is important is that in the numerator of the first expression, since it changes the sign of the time variable. We saw that this change made the time go backwards in the axis rotation representation. Then it was shown that since this time inversion did not affect the geometric relationship between the different quantities, it was possible to deduce, using simple Euclidean geometry, the different relativistic effects such as the time dilation, the length contraction, the velocity addition formula, and the twin paradox, by representing different inertial frames of reference as different rotated axes. As seen before, the equations of the circle change to hyperbolic when seen from an internal perspective, that is, when we are a part of the structure. Now we wonder how the simple harmonic motion is seen from within too. Given a uniform circular motion, it is well known that its projection on the x-axis gives a simple harmonic motion. To calculate the value of the velocity and the acceleration of the simple harmonic motion, one needs to differentiate the position with respect to the time tau. Let us now look at the same motion, but now from an internal perspective by multiplying all the values of y by the imaginary unit I and substituting y by ct. Thus, bearing in mind that the derivative of the star sine and star cosine functions are the same ones as the normal ones, but with an added imaginary unit, one can obtain the expression of the velocity, which will be called v sub tau, and also that of the acceleration, the a sub tau. Note that this sub tau acceleration has changed its sign with respect to the conventional one. This difference will be relevant in later chapters. And now we wonder, do these two magnitudes have any physical meaning? In principle, they are the internal view of the velocity and the acceleration that results from projecting the fundamental cycle on the x-axis. But what physical significance do they have? Are they observable? To interpret them physically, it might be more inconvenient to differentiate with respect to the time coordinate t rather than with respect to tau, since we still do not know exactly what tau is. In this way, we differentiate the position with respect to t using two derivatives with respect to tau above and below. Since omega cancels out, we re-express the argument in terms of the original alpha angle. Note that this expression was already defined in the first video as the velocity v sub g. In fact, we already knew that v sub g was the derivative of x with respect to t. Does this expression provide any information about the sub tau velocity? Not yet, but since we know that the v sub tau is proportional to minus I star sign, we can rearrange this expression leaving the minus I star sign all alone on the right. Then we multiply on both sides by the rest mass. Since the star cosine is equal to the Lorentz factor, we find that the left side of this expression is the relativistic momentum p. Then, since the right part is proportional to the v sub tau, we have that the relativistic momentum p and the v sub tau are proportional, which is great. Let's look at the case of the acceleration now. Let's first remind the expression of the time and the momentum. The sub-tau acceleration is proportional to the star cosine. Can any cosine appear from the momentum? Yes, we can differentiate the momentum to make its sign become a cosine. So here we go. Oops, our cosine are cancelled out. To find something proportional to the cosine, we can multiply on both sides by x, since x is r times the cosine. We see in this way that the left side is directly the definition of energy, and the right side, since the star cosine is the Lorentz factor, is directly the relativistic energy, which, since it is proportional to the cosine, one can state that it is also proportional to the acceleration of the simple harmonic motion. Therefore, although we still do not know the proportionality factors between the relativistic momentum and the velocity and between the relativistic energy and the acceleration, we can already state that they are interpretable in terms of a simple harmonic motion, which is great. Let's go further now. We first group the results by writing down those expressions of the time, the position, the momentum and the energy that were already found. And now we wonder, if the velocity and the acceleration in the conventional simple harmonic motion are consecutive derivatives of x with respect to tau, can something similar happen in our case of the position, the momentum and the energy? Note that if one assumes that the linear rotational velocity associated with the fundamental cycle is the speed of light, then the omega becomes c over r. Thus, let omega be substituted in all expressions by c over r. In this way, the position x becomes r times the derivative of t with respect to tau. The momentum is m times the derivative of x, and the energy is r times the derivative of the momentum. However, the most interesting thing to see is that setting the linear velocity to be the speed of light makes the derivative of t with respect to tau be directly the Lorentz factor, which is a well-known result in relativity. Then, If t is the time coordinate, then tau must be the proper time, which is great. Therefore, according to these expressions of time, position, momentum, and energy, it seems that there are two different wheels, that of the space-time and that of the energy momentum. The first has radius r, and the second a radius equal to the mass c squared. We do not know, however, what the relationship is between these two different radius. That's future work. Now, with the help of this trigonometric expression, one can find the EP relation. Interestingly, this expression comes from a triangle where the two legs are E and CP, and where the hypotenuse is the mass per c squared. This means that the energy, rather than being the total energy, should be interpreted as a kind of potential energy. This observation will be useful for the following chapters. Finally, if we substitute these expressions of the momentum and the energy as a function of the velocity and the acceleration of the simple harmonic motion in the EP relation, the EP relation becomes, except for a sign, the expression acceleration velocity of the conventional simple harmonic motion. And we already know where this difference in sign comes from. It comes from the fact that we are looking at the structure from the inside. Therefore, the EP relation is nothing more than an internal view of the acceleration-velocity relation of the conventional simple harmonic motion. Per tant, fixeu-vos que estem trobant. Estem veient que l'energia, el moment, la posició, el temps, tots estan definits sobre el cercle. O sigui, estem parlant una i altra vegada sobre el cercle. La física és el cercle, és l'estudi del cercle, però és un estudi des de dins l'estructura. O sigui, el fet d'incloure'ns des de dins l'estructura ha fet entrar la unitat imaginària, i la unitat imaginària és el que ha convertit l'aspecte de cercle en l'aspecte d'una hipèrbola. I per això la relativitat ens sembla estranya d'entrada, però en el fons és l'estudi del cercle, i per mi això em sembla meravellós. Per cert, aquí cal afegir dues coses, i una és que hem trobat la velocitat de rotació del cicle fonamental, que era l'omega era c partit per r, això és una dada important que ens farà falta per més endavant, i una altra és que, una cosa important també, és que l'acceleració del moviment harmònic simple vista des de dins l'estructura ha canviat el signe respecte a l'acceleració del moviment harmònic simple convencional. O sigui, en lloc d'apuntar sempre cap al centre del gir, és una acceleració que ens apunta sempre cap a fora del gir. I això resultarà important quan tractem la gravetat.